Everybody, depending on where you are now. Welcome to the week 4 of Focus program in Fields Institute in Virtual Fields Institute on analytic function spaces in the application. And this week will be devoted to model spaces. And it's my pleasure to introduce our first speaker today, Stephan Garcia from Pomona College, who will start his mini course on model spaces. Welcome.
Thank you. Hope everyone can hear me. I'd like to thank the organizers for having me, and I'd like to thank everyone here for continuing to attend these wonderful series of talks. So the numbering that you're going to see here refers to the book chapter or paper that I believe Javad will send a link to at some point. So for those of you interested in following along, everything is numbered, and you can look back at that chapter that'll be posted as a PDF quite soon. So it's a quick overview. Model spaces are the backward shift invariant subspaces of the Hardy space H2. We're going to be interested in them because of their very interesting function theoretic behavior and also their connections to operator theory. So what we're going to see in these 3 lectures are a very brief and selective overview of the theory of model spaces. And I'm aiming this particularly at the novice rather than someone who's experienced in this. So you know, if you're an expert in this, these lectures will probably appear quite elementary or superficial, but I'm trying to keep things short and suppress some of the difficult details because they're going to be pushed off to the references. And I'll often focus on very instructive finite dimensional examples because that's when you can really get your hands dirty and start understanding things, because things get rapidly much more difficult to deal with in the infinite dimensional case. So I always think you need a grounding in the simple examples before you move on to things that are more complicated. Now, another disclaimer is that we're going to focus on model spaces themselves rather than operators that interact with them. We'll consider some operators, but for example, Hankel operators and truncated Toeplitz operators won't appear in these lectures because, of course, those will be covered by some of the other lecturers. So this is not a comprehensive overview of everything connected to model spaces, but sort of a brief and selective survey. And so I need to go over a few preliminaries just to get our notation straight. A lot of this was covered in the first series of lectures by Javad. And so this is mostly notation, a refresher on Hardy space theory. So I'm going to assume that the audience is familiar with the Lebesgue spaces capital L2 and capital L infinity on the unit circle, which I'm going to denote by T. We're going to let Z denote the integers. Little L2 of Z, that's going to be the space of square summable sequences. M is going to be normalized Lebesgue measure, and the open unit disk is going to be D. So pretty standard notation. Let's recall Parseval's theorem, which says that the capital L2 norm of a function on the circle is equal to the little L2 norm of the sequence of Fourier coefficients of that function. The Hardy space, you may recall, is going to be the set of all analytic functions on the open unit disk D, so that these integral means remain bounded as R tends to 1 from below. Again, I'm going to go through this rather quickly because I'm assuming that everyone has attended that first series of lectures on the Hardy space. So for each Hardy space function, little f, the non-tangential limit exists for almost every boundary point on the unit circle. And so we can consider the boundary function, which we're also going to denote little f. And it turns out that that boundary function of an H2 function also belongs to L2, and we have an equality of norm. So for every function f in little h2, we have this really, really nice connection here. The value of the boundary function at zeta, for almost every zeta on the unit circle, basically looks like plugging in zeta into the power series representation for the function little f. And in fact, the nth Fourier coefficients, which I denote here with f hat of n, actually equals the nth Taylor coefficient for f at the origin, which is what we're saying here. And the way you want to think of H2 when we're thinking of it in terms of Fourier analysis, it consists of those Fourier series in capital L2 with no negatively indexed terms. And so we're going to think of H2 as a subspace, a norm-closed linear submanifold of capital L2, and capital H2 then becomes a Hilbert space endowed with this inner product that's compatible with the L2 inner product. You can compute things on the boundary. You can look at the boundary functions of H2 functions, compute the inner product there, or we can take a look at the Fourier coefficients, or slash Taylor coefficients at the origin with equality of inner products. Now, analogous definitions exist for the other Hardy spaces HP, where P is between 1 and infinity. P equals infinity is a special case. In that case, we get the algebra H infinity of all bounded analytic functions, and that's going to come endowed with the supremum norm. And it turns out the boundary function of an H2 function belongs to L infinity, the bounded measurable functions on the circle. And we have, again, equality of norms, and we're going to regard H infinity as a Banach subalgebra of L infinity. Now, another thing I'm going to need you to recall about the Hardy space that we're going to use over and over again is the reproducing property. And so this function here, which I'm going to denote C sub lambda, where lambda is in the unit disk, that is going to be the Cauchy kernel, also called the Szego kernel. And it has the remarkable property that it reproduces the value of a Hardy space function at lambda. So in other words, f of lambda is equal to f inner producted with this kernel. It's the reproducing kernel of H2, the Cauchy kernel slash Szego kernel. And in particular, we're going to use this fact over and over again. A function vanishes at lambda if and only if f is orthogonal to the corresponding Cauchy kernel. And you can see that from this formula right here. We'll also use and more refer to obliquely the derivative kernels. So what happens, you also have reproducing kernels for the derivatives of your function. So the nth derivative of a Hardy space function at lambda is given by taking the inner product of your function against this sort of modified Cauchy kernels, just the derivative of C lambda with respect to Z, the appropriate number of times. Another important fact, these Cauchy kernels are linearly independent, and that's going to figure quite prominently into our study of finite dimensional model spaces. So if you have a distinct sequence of points in the disk, you take a look at the corresponding Cauchy kernels, they turn out to be linearly independent. And I think aside from inner-outer factorization, we're almost going to have everything needed to start dealing with model spaces. So in fact, there's going to be a whole lecture coming up on inner functions, I believe, although inner functions were covered in that first series of lectures. We're going to look into them in much greater detail in some of the later lectures coming up in this lecture series, not mine, but one of the other speakers. So I'm just going to need you to recall really briefly, an inner function is a bounded analytic function that has unimodular boundary values almost everywhere on the circle. And so you may recall that these come in a variety of flavors. They are, well, unimodular constants times a possible power of Z times a Blaschke product. So that is a product of disk automorphisms set up in such a way that it maps the disk to the disk and the circle almost everywhere to the circle. And you have to have these zeros of this so-called Blaschke product satisfy the Blaschke condition. They have to tend to the circle rapidly enough to ensure convergence. And then we also have this singular inner factor that arises from a non-negative singular measure over here. And so that is a typical inner function. An outer function, I hope you will recall, it's a function of this form here, where phi is an L1 function that is real valued, and gamma here is a constant. So we have a unimodular constant times this complicated expression here. The point of this is that with inner and outer functions, we have unique factorization in H2, and that's something that we're going to use very frequently. A non-zero function in H2 has a unique factorization of the form BSF, where B is a Blaschke product, S is a singular inner function, and F is an outer function, which happens to be in H2. And conversely, any product of things of this form belongs to H2. So an analogous factorization holds for HP, where the modification is the outer factor of F belongs to HP instead of H2. So now, with all of that in hand, we can get on to model spaces. The model space corresponding to a non-constant inner function U is this thing. You basically take H2, multiply every function in H2 by U, that gives you a subspace of H2. Then you take the orthogonal complement in H2, and that is going to give you a subspace of H2 called the model space corresponding to U, and it's denoted script K sub U. So again, that's the orthogonal complement of this sort of Berling type subspace UH2, the set of all function is H2 multiplied by the inner function U. So interesting fact that one can derive from the definition that A model space contains the constant functions if and only if the inner function vanishes at the origin. And in many applications, one sort of sets things up so that U vanishes at the origin. This will come up quite a bit later. So just remember, the model space contains the constant functions if and only if the inner function vanishes at the origin. It's a little bit of a philosophical problem with model spaces, however, and that is that our definition is a little bit indirect. We're defining a model space to be the orthogonal complement of a very, very concrete subspace. So consequently, it can be a little bit difficult to determine whether a function belongs to a model space or not, or characterizing the functions that belong in model spaces. And so, fortunately, in the finite dimensional case, well, model spaces are explicitly realizable as concrete spaces of rational functions. It's in the infinite dimensional case that model spaces take quite a bit more work to understand because of this negative characterization as an orthocomplement of something. So you may recall from Berling's theorem that the non-zero invariant subspaces for the unilateral or forward shift operator, where we take F and just multiply it by Z, well, the invariant subspaces of H2 for this shift operator are these Berling type subspaces, UH2, where U is inner. Right? So it turns out, because of this orthogonal complement characterization of model spaces, that the model spaces are the invariant subspaces for the backward shift operator on H2. So that is this operator, which I'm denoting S star, which has this funny definition where you subtract off the value of F at the origin, so that now the numerator vanishes at the origin, so I can divide by Z. That turns out to be the backward shift operator on H2. And it is the adjoint of the forward shift because one can verify that the inner product of SF and G is the same as the inner product of F with S star G for any H2 functions F and G. Now, this is understandable quite a bit better in terms of Taylor coefficients. When you look at things in terms of Taylor coefficients at the origin, well, the forward shift operator is just shift forward and insert a 0 here at the front. The backward shift is, as its name implies, the backward shift. You just chop off a 0 and shift things to the left. So you shift in the backwards direction. So the model spaces are the backward shift invariant subspaces of H2. That is the point here. Now, let me give you a couple basic containment properties here. How do model spaces relate to each other? If U and V are non-constant inner functions, we're going to say that U divides V, denoted U slash V, if the quotient V divided by U belongs to H2. Now, because of the inner function factorization theory, one can characterize exactly when that happens in terms of singular inner functions and Blaschke factors, but we will just leave it at this. The point is U divides V if and only if V divides U happens to be an inner function in H2, right? Or happens to be an inner function at all. Now, the containment of model spaces reflects the factorization of inner functions in a very natural and nice way. An inner function U divides an inner function V if and only if the model space KU is a subspace of the model space KV. So that's a short exercise to prove, but it basically says that the factorization of inner functions is perfectly reflected in the containment of model spaces. And this is something we'll use on occasion. The perspective that we're trying to develop and that we'll use over and over again in these talks is that it pays not to think of H2 as its own thing, but to think of H2 as sitting in this larger ambient space, capital L2. So in other words, we tend not to think of H2 as a collection of analytic functions on the open unit disk. We tend to think about the boundary values of H2 functions on the circle and work on the circle as much as possible. And we'll see this in the next slide. So this interplay between analytic functions on the disk and their boundary values on T in this context of the larger ambient space, capital L2, is a very, very, very common thing. And so, first proposition here. In terms of boundary functions, we can characterize the model space KU. It is H2, thinking of this as a subspace of capital L2 of the circle, it's H2 intersect this thing. So this makes no sense when you think about this in terms of analytic functions on the disk, because it looks like this is not analytic. But again, we're thinking about things on the boundary. So we're thinking about Fourier series on the boundary. So you think of H2 as Fourier series with non-negatively indexed coefficients. So what we have is H2 bar times Z bar. So in other words, this Z bar, H2 bar, that is the L2 functions with negative Fourier terms only. So we think of Ku as this. It's a strange thing. You take this inner function U, multiply it by ZH2 bar, the negatively indexed Fourier function, or Fourier series, multiply it by U, which is an analytic function that jumbles things up, and you get this weird subspace of capital L2 over here. You intersect it with H2, that happens to be the model space Ku. It's a strange way of operating if you're not used to dealing with pushing things to the boundary and working in this larger ambient space. So here's the explanation. Let F be an H2 function. We know that U times U bar is equal to 1 almost everywhere because U is an inner function. It has modulus 1 almost everywhere on the circle. And so F happens to be orthogonal to UH2, or in other words, to belong to the model space Ku, if and only if, well, what I do here is I can move the U from one side to the other inside an inner product because U times U bar is equal to 1. So F is orthogonal to UH2 if and only if U bar F is orthogonal to H2. So what you need to do is write the relevant inner products in terms of integrals on the circle, use the fact that U bar is equal to 1. That's what's going on here. And what this means here is, okay, if I've got an L2 function that's orthogonal to all of H2, think in terms of Fourier series, that means you can't contain any non-negatively indexed Fourier terms. In other words, you must consist entirely of negatively indexed Fourier terms. So in other words, you must belong to ZH2 bar, right? So what that tells me is that, well, F belongs to the model space Ku, the ortho complement of UH2, if and only if F happens to belong to, well, what am I doing here? I'm multiplying both sides of this expression by U. So I get if and only if F is an element of U times ZH2 bar. So it's kind of an interesting thing. We've got a characterization in terms of boundary functions, thinking in terms of L2. So an important observation here is that F belongs to the model space Ku if and only if, well, we go back here, right? F has to look like this, right? It has to be something of this form. So in other words, there has to be some companion function G in H2 so that F, this function in H2, happens to be equal to U times ZG bar. And again, those of you used to working entirely in the disk, this looks totally wrong. But remember, this is happening on the boundary, not on the interior of the disk. This is happening in capital L2 of the circle. And it just so happens for some H2 functions, this weird expression happens to multiply out and actually yield the boundary values of another H2 function. Strange, it's unusual, but it works out. So we need to take a look at the reproducing kernels for model spaces. So if F is in Ku and lambda is in D, we're going to derive the formula for the reproducing kernel as follows. Well, the Cauchy kernel, you'll recall, reproduces the value of any H2 function at lambda. So this is just the property of the Cauchy kernel. What I'm going to do next is say, well, I can subtract off this bit because F is in the model space. So that means F is orthogonal to everything in UH2. So what I have here is U times some H2 function. So this inner product is 0. So I'm allowed to tack this on. And so I regroup terms as my next step. And so I have F times F inner product with this thing is equal to F of lambda. So I'm going to call this weird expression K lambda. So this happens to be the reproducing kernel for the model space Ku. You can see the Cauchy kernel part right here, 1 over 1 minus lambda bar Z. And then we've got this extra part here that contains information about the inner function U. So we'll notice it's an outer function in H infinity. So it's an invertible outer function in H infinity. We'll use that in the second lecture. It belongs to Ku. So in other words, it is actually the reproducing kernel we're looking for because it has the reproducing property and it belongs to Ku because of the following computation. Well, how do you show membership in script Ku? You show that you're orthogonal to every function of the form UH. So you're orthogonal to U capital H2. And the way you do that is as follows. Well, use the formula for K lambda and split things up. And so UH inner product K lambda is, well, it is U lambda H lambda minus U lambda times the inner product of H with C lambda. We use the fact that C lambda is the reproducing kernel for any H2 function. And so that tells me that we're just subtracting the same thing from itself and we get 0. So moral of the story, K lambda is orthogonal to everything in U capital H2. So that means K lambda is in the model space script Ku. So that is our reproducing kernel. This formula here is going to be very, 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 very important for what we do. And those of you who are used to other types of operator theory, multivariable operator theory, higher dimensional things, you'll recognize that kernels of this form appear quite a lot in operator theory, and sort of model spaces are sort of the basic first time you see kernels that have this sort of appearance. And so let's take a look at the orthogonal projection from the big space, capital L2, onto the model space script Ku. So yeah, this is a standard fact that applies for any reproducing kernel Hilbert space. But if I want to compute the value of P sub U of F, so if I want to take some function F in L2 and project it into the model space script Ku, well, I do that by just taking the inner product of F against K lambda, where K lambda is the model space reproducing kernel, and that just gives me the value of P sub U of F at lambda. And here's why. And so again, this argument is quite general, but I want to run through it because there's a lot of things for students to get from this argument. We're going to note that an orthogonal projection is self-adjoint. And so that means once it's inside of an inner product, we can move it from one side to the other without changing anything. That is a legal maneuver. So F comma K lambda is going to be F comma PU times K lambda. The reason is PU is the orthogonal projection onto KU. So that means this orthogonal projection fixes every function in the model space. So K lambda is P times K lambda. And then I use self-adjointness. I move this orthogonal projection from one side to the other inside the inner product. And then what do? I have P sub U of F, which is something in the model space. I don't know exactly what it is, but it's in the model space. So the reproducing kernel for the model space certainly reproduces the value of this function P sub U of F at the point lambda. And again, this is a general argument that applies for reproducing kernel Hilbert spaces, but it involves some important ingredients. So what I can finally get to now are some characterizations of finite dimensional model spaces. And these are the model spaces for which we have a very, very nice concrete description. So here's an important fact. You'll recall that U of H, right, that is some Hardy space function. So the Cauchy kernel, the Cauchy-Szego kernel reproduces its values. So since U of H inner product C lambda equals U lambda H lambda for any H2 function, little h, what we can tell here is that, okay, you are orthogonal, this Cauchy kernel C lambda belongs to Ku. In other words, C lambda is orthogonal to every function of the form UH, if and only if, well, look at what happens over here. If this is 0 for every function H in capital H2, that's the same thing as saying that U of lambda must be 0. So the important fact is a Cauchy-Szego kernel belongs to Ku if and only if the inner function U vanishes at the corresponding point lambda. Very, very important point, and that will lead us to the next proposition. Again, the numbering here refers to the numbering in the book chapter, which I believe the link to will be posted quite soon if it hasn't been posted in the chat already. So the result here is, if you've got a finite Blaschke product with zeros lambda 1 up to lambda n, you can write down every function in the corresponding model space Ku. it looks like this. You got a polynomial of degree at most n-1 in the top, and then you've got these factors in the bottom. And these are the sort of factors that look kind of familiar because those appear in the denominators of Cauchy kernels and the reproducing kernel for Ku. So we basically have kind of like a weighted polynomial space, but in particular, this is a space of rational functions, a very concrete space of rational functions. And in the case where you stack all of the zeros of your Blaschke product at the origin, or in other words, U is of the form Z to the N, well, then all of these things in the denominator just disappear and you actually just have an honest space of polynomials. So here's the explanation, and I'm going to focus on the case with simple zeros. To do the more general case, you just use the derivative kernels. So, the details of that I'll push off into the book chapter if you want to see the details. I want to focus on the simplest version of each argument. So let's suppose that U has only simple zeros, no repeated roots. Now, this comment above about when a Cauchy kernel is contained in a model space, well, that tells us that each of the Cauchy kernels corresponding to the zeros of U belongs to the model space. So their span belongs to the model space Ku. So we just need to look at that reverse containment. And so we note the following. Let's suppose that F vanishes at lambda I at one of the roots of the inner function U. In other words, F is orthogonal to the Cauchy kernel at lambda I for each of the zeros of U. Well, okay, if F vanishes at each of the zeros of U, Hardy space theory tells me that the finite Blaschke product U has to be a divisor of F, right? So U divides F. And in other words, F is of the form U times some H2 function. So F is in UH2. And what that tells me is that, well, oh wait, UH2, that's the orthogonal complement of the model space. Right? That's how you define model spaces. They're the orthogonal complements of subspaces of the form UH2. And so that tells us that the orthogonal complement of the span of the Cauchy kernels corresponding to the zeros of the inner function U is a subspace of UH2. And UH2 is the orthogonal complement of the model space Ku. And so when you take orthogonal complements of this line, you get a containment in both directions. And so you say, the model space Ku is just the span of those n Cauchy kernels. So the model space is automatically there, a subspace of rational functions. You know exactly where the poles are in their multiplicities. And so if you take a look at the span of these Cauchy kernels, use a partial fractions argument, you can see, well, when I collect things together, I'm going to get exactly something of this form. So this is a nice characterization of model spaces corresponding to finite Blaschke products, at least in the case with simple zeros. For repeated roots, you deal with not necessarily just the reproducing kernels, but also derivatives of reproducing kernels. But again, I'll leave that to your imagination. So generalization of that argument says that if I've got a finite Blaschke product with distinct zeros, Z1 up to ZD, where now I'm allowing the possibility of multiplicities, and I'll denote the multiplicities M1 up to MD, then the same sort of argument says, well, Ku is just the span of a bunch of Cauchy kernels and the appropriate derivatives. So the derivatives up to a certain order here, right? So that's the generalization that I was speaking of the preceding result. Now, the thing I want us to recognize here is that this is possible really only because we've got a finite Blaschke product. If we had an infinite Blaschke product, I have issues of convergence in that denominator from the preceding slide. If I've got a singular inner function, I have no idea what's going to happen here. So these finite dimensional model spaces occur if and only if the inner function is a finite Blaschke product. And there's an explanation for why this occurs. So what we really need to show that the model space is infinite dimensional whenever U happens to not be a finite Blaschke product. And there's a couple ways that can happen. If U has an infinite Blaschke factor, well, then that means U has infinitely many zeros, right? So by what we've seen in the previous slides, you take a look at the Cauchy kernels corresponding to those infinitely many zeros. Cauchy kernels are linearly independent. So that means your model space contains an infinite linearly independent set, right? Once you have infinitely many zeros, infinitely many linearly independent Cauchy kernels, and you're done, infinite dimensional. Now, if U has a singular inner factor S, well, what you can check is that, well, the subspaces of Ku correspond to the inner divisors of U. So S is an inner divisor of U, but also the nth root of that singular inner function is also an inner divisor of U. So that means Ku contains an infinite chain of distinct subspaces. And that means that that model space Ku is infinite dimensional. So in either case, you're going to be infinite dimensional. The model space is finite dimensional if and only if it comes from a Blaschke product. Okay, now I want to tell you about the relationship between model spaces and Toeplitz operators, or at least conjugate analytic Toeplitz operators. That's going to involve the Riesz projection. Again, we're working in capital L2. We're thinking of H2 and all the model spaces is sitting inside capital L2. So I'm going to let P be the orthogonal projection, the Riesz projection from the big space L2 onto H2. So as an orthogonal projection, it's self-adjoint and idempotent. And in terms of Fourier coefficients, what you're really doing is you're taking this Fourier series in capital L2 that's indexed by the integers, and I've highlighted the 0th coefficient, and you're chopping off all the negative stuff, right? And that gives you a sequence of non-negatively indexed Fourier terms that corresponds to the Taylor coefficients of an H2 function, or in other words, the Fourier coefficients of an H2 function. And so what the Riesz projection does is kind of interesting. Here's an example. So we start with e to the I theta, and we're going to identify that with z, a complex variable on the unit circle. And if I have this L2 function, 1 plus 2 cosine theta, and I want to project that into H2 and find out what I get, I do it this way. I say, well, 2 cosine theta, that's e to the I theta plus e to the minus I theta, okay, plus z. So now I've kind of got my Fourier series here. I've got a negatively indexed Fourier term, and the Riesz projection is going to kill that off. So I just get 1 plus e to the I theta, or in other words, when I think back in terms of complex variables, 1 plus z. So you see we can project something in capital L2 and recover an analytic function in capital H2 from it. And this is a similar computation to what we saw before when we were projecting into model spaces. Since P is equal to P star and the Cauchy kernel belongs to H2, same sort of computation says that I can compute the Riesz projection of F at lambda by just taking the inner product of this function, which is in L2, with the corresponding Cauchy kernel. And if I wanted to, I could write this in terms of integrals and in fact get a Cauchy integral type of representation for the Riesz projection operator. So now I need to tell you a little bit about Toeplitz operators. These will be covered in a lot more detail in a future lecture on operators on function spaces. But for right now, I think we can just cover what we need here. So the Toeplitz operator with symbol phi in L infinity is the map that goes from H2 to H2 defined as follows. You basically multiply your function by phi, and that's going to be some function in capital L2 now, and then you're going to project it back into the Hardy space. So you start with a Hardy space function, multiply it by some bounded measurable function, and you get something in L2. Put that back in H2 by projection. And so if the symbol is an H infinity, then you actually don't even need the projection. And this is what's called an analytic Toeplitz operator. We're going to be more interested when the symbol has the conjugate in H infinity, and that's going to be called a co-analytic Toeplitz operator. Those are going to be the ones that are more important for us right now. And again, Toeplitz operators, they'll appear in more detail in later lectures. What we need to know now is, and this is a good exercise for students, prove that the adjoint of the Toeplitz operator with symbol phi is the Toeplitz operator with symbol phi bar. We're going to need this little fact. And here's a connection with shift operators. The unilateral shift, which is just multiplication by z, is the Toeplitz operator tz. You basically just multiply by z and you don't need to project because you're already in H2. Now, if phi is in H infinity, the bounded analytic functions, then one can sort of come up with a functional calculus in this fashion. I can say, well, phi of the operator tz is going to be the Toeplitz operator t sub phi. And it turns out that this respects and extends the standard polynomial functional calculus. Now, there's a lot of details to fill in there, but one can actually prove that this is isometric. The norm of T sub phi is actually the norm of phi in H infinity. So in other words, one can regard these analytic Toeplitz operators as analytic functions of the shift operator, analytic functions of T sub z. On the other hand, the backward shift, which is the adjoint of the forward shift, well, that's going to be T of z bar. And so now that we've got these definitions about Toeplitz operators, we can examine how conjugate analytic Toeplitz operators relate to model spaces. So first of all, model spaces are invariant under conjugate analytic Toeplitz operators. If you apply a conjugate analytic Toeplitz operator to a model space, you wind up in the same model space. And here's why. Again, cute computations on the boundary, working with Fourier stuff on the boundary circle as opposed to dealing with analytic functions in the disk. So if I've got a model space function f, and I have a little h in capital H2, we do this computation. T sub phi bar of f, well, let's check its inner product against UH. Find out when it's 0. Well, because the adjoint of T phi bar is T phi, we can move it to the other side of the inner product. The definition of the Toeplitz operator says multiply by phi and then apply the Riesz projection operator. So that's what I've got here. Now I use self-adjointness of the Riesz projection to move the p from one side to the other. And I say, okay, well, f is in the model space, so that means f is already in capital H2. So that means the Riesz projection fixes f. So I can basically just drop the p there. And now I have f inner product u times something. What is this something? It's an H2 because phi is a bounded analytic function. F is in the model space, so that inner product is 0. So what does this tell me? This tells me that T phi bar times f is orthogonal to any function of the form UH. That tells me that T phi bar times f belongs to the model space KU, and that gives me this invariance under conjugate analytic Toeplitz operators. So those of you who deal with Banach spaces of analytic functions might recognize this stability under removal of inner factors as, maybe I've gone ahead of myself, but the following thing we'll see is called the F property when you study Banach spaces of analytic functions, because a consequence of the previous proposition is that you can strip off inner factors of functions in model spaces. You can just remove them. Model spaces are invariant under removal of inner factors. So precise statement is this: if theta is an inner function, and f over theta happens to belong in H2, where f, of course, belongs to the model space Ku, then I can just remove that inner factor. F divided by theta also belongs to Ku. So what this means, if you take it to the logical extreme, you can remove the inner factor of f. You can just strip it off completely. So the outer factor of a function in a model space belongs to the same model space. So you can basically keep removing inner factors until you just get to the outer factor at the end. And all of the functions that you had in between also belong to the model space. And so here's how we do it. Again, playing around with projections and boundary functions. So take a look at T theta bar. So in other words, the projection, the Riesz projection of theta bar f. Well, since I'm on the circle, theta bar makes sense. Theta bar is 1 over theta on the circle. So this is, I can write as f over theta, but I'm saying by hypothesis that f divided by theta is an H2 because theta is an inner factor of f. So the projection does nothing because I'm already in H2. And so what this tells me is that, well, I am going to be in the model space because we just said that the model space is invariant under any conjugate analytic Toeplitz operator. So it's a very important thing. The outer factor of a function in a model space belongs to the same model space. You can remove inner factors at will. So I'm going to get on to the final topic of the day, and that is the compressed shift operator. So we're going to recall that PU, that is the orthogonal, that's not the Riesz projection. The subscript U is denoting that this is the orthogonal projection from L2 onto the model space, not H2. What we want to do is take a look at our favorite operator, the shift operator, and squeeze it down, compress it to the model space, and look what happens there. And it's very, very, very interesting. And in fact, there's a whole series of lectures coming on later on in this lecture series on truncated Toeplitz operators. That's toward the end of the program, but it's all basically all based on this particular operator. So you could really take this operator and run with it. The compressed shift is going to be, well, you perform the shift, multiply by z, and then project back into the model space, because multiplying by z probably takes you out of the model space. Model spaces are backward shift invariant, not forward shift invariant. So we got to project to get back into the model space. And that's going to give me the compressed shift operator a sub z, and then the superscript u just tells you what model space you're on. So we're usually going to write a sub z because we're going to know what the inner function u is from context. Now, the important thing is that this works out pretty nicely. There's sort of there's a nice polynomial functional calculus here, and you can go beyond that. The nth power of the compressed shift is really the compression of, well, maybe okay, maybe I didn't define what this notation would mean, but well, stay tuned for the truncated Toeplitz operator lectures. I don't want to dwell on this since I didn't define what it means to put a symbol down there. But that would be a truncated Toeplitz operator with symbol z to the n. Now, if you like the backward shift more, you can always work with a backward shift, because it turns out this compression of the shift operator to a model space is actually the backward shift restricted to a different model space. And that's sort of strange, because normally we think of the forward shift and the backward shift as operating as being very, very, very different operators. They have very, very different properties. They're adjoints of each other, but they're weird operators, and they're the standard counterexamples for basically everything. But it turns out when you look at their compressions, they're more or less the same thing. So the compressed shift on the model space Ku happens to be unitarily equivalent to the restriction of the backward shift, right, to Kv, where Kv, or where V is the inner function that you get by just conjugating the coefficients of U. Sort of a strange thing. So the backward shift and the forward shift really are more or less the same when you're dealing with model spaces. You just change the model space a little bit and you have essentially the same operator. And sometimes it's better to work with a backward shift because the model spaces are backward shift invariant. They're not forward shift invariant. You have to put a projection if you want to deal with that. So sometimes it's better to deal with a backward shift because model spaces are already backward shift invariant, S star invariant. So that's one reason you might change perspective and deal with the backward shift. So I need to tell you about the spectrum of these operators. This is where the function theory of the model space interacts with operator theory of the compressed shift. So we're going to need to define the spectrum of an inner function. The spectrum of an inner function is the lim-inf zero set. It's going to be the set of points in the closed unit disk where this limit inferior is equal to 0. And there's a couple ways you can sneak into this set.
I have to. I'm tuned into this other talk by Stephan Garcia. Let me see a minute. What I'm doing. I can't.
I believe that's not meant to be a question. Okay, so I'll continue. I'll deal with questions if there is a question afterwards. So the spectrum of an inner function is defined to be this set. And it's called the spectrum for a very good reason. It turns out to be the spectrum of the compressed shift associated to U. How do you get in the spectrum of an inner function? Okay, well, the zeros of U are automatically in here. Also, the accumulation points on the unit circle of the zeros of U are going to be in this lim-inf zero set. A little bit harder to see is that the support of the singular measure that arises from the singular inner factor of U is also in the spectrum. And it turns out that that's basically it. And an important theorem here, Lifshitz-Miller theorem, says that if U is written as a Blaschke product with zero sequence lambda and singular inner factor S sub mu, where mu is a singular measure, then the spectrum of the compressed shift on that model space equals the spectrum of the inner function as defined up above, which is, of course, why they called it the spectrum of the inner function. And it turns out the spectrum of the inner function is what you think it should be. Well, how do you get here? We only have two ways that we know how to get there. You're in the closure of the zero set of the Blaschke factor, or you're in the support of the measure from the singular inner factor. The other result here is that the point spectrum, the set of eigenvalues of the compressed shift is the zero sequence of the Blaschke factor. So here's sup u, that's the support of the measure mu. So this is a really interesting result. Basically tells you all about the spectrum and the spectral properties of the compressed shift and relates it to the function theory of that particular inner function. It's really, really elegant result. So what I'd like to end on is a really, really cool result that tells you why these things are called model spaces. It's going to require a little bit of setup, but it's sort of going to be the big bang at the end. So we're going to let H now denote a separable complex Hilbert space, an abstract Hilbert space. B of H is going to be the set of bounded linear operators on H. And we're going to let squiggle equal denote unitary equivalence. So we're now not thinking about H2, we're dealing with abstract Hilbert spaces. So let's suppose that T is a contraction on H. In other words, its operator norm is at most 1. It turns out that you can get a direct sum decomposition of T in a very, very nice way. T can be written as the direct sum of two operators, one of which is unitary. Now, might not actually exist, but this is the generic case here. And K is something called a completely non-unitary contraction. Again, either sum and could be absent for a particular T. So we have two types of contractions that we can split into: unitaries, which we're pretty comfortable with, and then these completely non-unitary contractions. So those are contractions which don't have a reducing subspace upon which K happens to be unitary. So K is completely non-unitary. CNU, if you cannot find a reducing subspace, a subspace invariant under K and its adjoint upon which K happens to be unitary. So you've stripped off all possible unitary parts of T and you've stuffed it into this factor, and what you're left with is something that is totally not unitary at all, and there's no reducing subspaces upon which that acts unitarily. So you split it into a good part and a bad part. So the reason we care about CNU contractions is because the spectral theorem tells us almost everything we could want to know about unitary operators. Right? Unitary operators are pretty much handled by the spectral theorem. It's the CNU part that we're interested in. And so here's a seminal theorem of Nagy-Foias, and it's a really, really beautiful theorem. And in fact, I was prepared to give the proof, although I'm sure I'm not going to have enough time. However, the proof is going to be in the notes and also in the slides, which I believe you will be provided. So if you want to see the details of this, I suggest you have a look. It's a really beautiful theorem, really beautiful, nice proof. And the theorem says this: I start with a bounded operator on a Hilbert space. I probably need that to be a contraction there. Okay, but let's suppose that the powers of T tend strongly to 0. So T to the n tends to 0 in the strong operator topology of script H. Or in other words, for every x, the norm of T to the nx tends to 0. Right? So it's really making things smaller eventually, right? Every vector eventually gets sent to 0 upon iteration by T, and you satisfy this defect 1 condition. In other words, T is close to being unitary. It's unitary-ish, but it's not, because if T were unitary, I minus T star T would be the 0 operator. I minus TT star would be the 0 operator, but I'm assuming it's not. But let's say it's close, that the rank of these two self-adjoint operators, it's not 0, but it's equal to 1. So we're kind of close to being unitary. We're unitary-ish. So if we satisfy these hypotheses, well, then it turns out T is basically the restriction of the backward shift to a model space. So out of this abstract hypothesis, T should be a contraction, satisfies the powers of T going strongly to 0, satisfies this so-called defect 1 condition or defect 1-1 condition. Then out of that abstract hypothesis, there exists a concrete inner function. There is an inner function U so that T is unitarily equivalent. So for all practical purposes, T is the backward shift restricted to the model space KU. So in other words, we have a functional model for defect 1-1 contraction. So contractive operators which satisfy this have a model, a concrete operator that we can identify this abstract operator with. We can say, well, if I want to study operators that have these properties, I should be doing some concrete function theory, and I should be looking at the backward shift on this model space, a concrete subspace of the Hardy space H2. So this is what I mean by a functional model, by model spaces. These spaces help us model certain abstract operators. And again, I would show you the proof, but I'm afraid I'm out of time. I will try and amend this to put the contraction hypothesis in there. But again, if you want to see any of the details, the slides will be provided to you, as well as the corresponding book chapter in the volume that I believe we are producing for this special season. And thanks for your attention.
Thank you very much. Let us thank the speaker. Any questions for Stephan? So just shout them out, because well, there are more than 100 participants. And let's see.
Now, I see some comments in the chat about people being unable to download the slides or the chapters.
Right. So Java just put another version. Let me try. Yes, it works. So the new version is downloadable. So try again.
I think the issue is you have to click on it and then wait for it to download. And then after it downloads, you have to click on it again and then it'll open. So,
yeah. So there is a question in the chat. If the rank is greater than 1, then is the result true?
Sure. Let me go back to the slides then. So the answer is yes and no. It's going to become more complicated and force you to consider a matrix or operator valued inner functions. And you can't even, in the case where these are equal, you basically have to deal with sort of matrix or operator valued inner functions. If they happen to be unequal, there are yet more complicated ways to handle things. But from my perspective, I really like the concrete function theory. And it turns out once you step away and start dealing with, matrix or operator valued inner functions, it's really, you don't have such a simple, nice way of saying, oh, Blaschke product, singular inner function, and it works out. Now, of course, there are substitutes for, Blaschke products and singular inner functions and those sort of things in these higher dimensional examples and higher dimensional settings, but they somehow, they're great, and they're probably about the best you could possibly do, but they're just not as concrete, and the function theory just happens to be a bit more abstract, because oftentimes you just can't write down like, oh, Blaschke product, the product of nice disk automorphisms that I can play with and use classical complex analysis tools on. So the answer is yes, there are many generalizations of this that apply for other pairs of defect indices, but none of them are as great and concrete as dealing with stuff in the classical Hardy space.
Thank you. There is another question in the chat. Does the restriction of a stat to any model space satisfy condition 1 and 2?
Yes, that is also true. I believe I have that in the book chapter as well. But it's something. I believe it'll follow from the proof also. But yeah, I suppose I should have said that it does sort of work the other way around. If you look at the restriction of the backward shift to a model space, it does satisfy both of these criteria.
Another question in the chat. What space do we obtain if we replace the Serge part of the model space reproducing kernel by the Bergman kernel?
That is a really good question. I'll have to punt on that question and probably give that to Stephan Richter or one of the other Bergman experts here. Now, my feeling is that most of this stuff falls apart because, as you can probably see, we're using the very special property that H2 is sitting inside capital L2, and we can deal with stuff on the boundary. Now, when you're dealing with the Bergman space, you don't necessarily have really nice, well-behaved boundary values that sit inside some larger, nice ambient space. So a lot of the tricks and techniques for model spaces probably don't work out as nicely. Now, I'm not saying that nothing works out, but I'm saying that it's probably going to be quite a bit different, just because that idea of just not even working on the disk, but just pushing everything to the boundary and dealing with Fourier series on the boundary just isn't going to work.
Thank you. More questions or comments? If not, let's thank Stephan again. And we have